Today we're going to talk about a technology that could completely reshape our digital world. It's called the quantum internet, and it promises something that sounds almost impossible, a truly unhackable connection. So let's dive in. But before we jump into the future, let's start with a question for you right now. Think about all your most private data, your bank accounts, your DMs, everything. We put a whole lot of faith in today's encryption to keep that stuff safe. But what if that entire system is built on a foundation that's about to crumble? Because here's the reality. The security we all rely on is facing a huge inevitable threat. The quantum computers that are being developed right now, they're not just a little bit faster. They represent a leap so massive that they could make our current methods of protection completely and totally obsolete. And here's the culprit. It's an algorithm called Shor's algorithm. You see, our current security is based on math problems that are just too hard for regular computers to solve in any reasonable amount of time. But for a quantum computer running this algorithm, it's like child's play. It's like having a master key to every digital lock on the planet. And this isn't some bug we can just patch. We need a fundamentally new kind of lock. So if our current rulebook for security is about to get thrown out the window, what do? Well, you don't just write a new version of the old rules. You find a completely different rulebook. And this one is written by the laws of physics itself. Everything starts with the most basic piece of information. We're all familiar with the classical bit, right? It's simple. It's either on or off, a 1 or a 0. But we're moving from that to something way more powerful and, frankly, way weirder, the quantum bit, or qubit. And this is where things get really fun. You see, a qubit can be a 0 or a 1, or it can be both at the same time. This is thanks to a bizarre property called superposition. The best analogy is a spinning coin. While it's spinning in the air, is it heads or tails? Well, it's kind of both, right? It only collapses into one definite state when you catch it and look. A qubit is just like that. It exists in this fuzzy combination of states until you measure it. That's the source of its power. And if superposition wasn't weird enough for you, get ready for entanglement. This is the phenomenon that was so strange, Einstein himself called it spooky action at a distance. This is when you can link two qubits so that they effectively become a single entity. Their fates are intertwined. What this means is, if you measure one of those entangled particles and find out it's spinning up, instantly that its partner is spinning down. And I mean instantly, even if that other particle is on the other side of the universe. It's not a signal traveling between them. It's like they share a single existence. And this bizarre, spooky connection is the absolute bedrock of the quantum internet. Okay, so spinning coins, spooky connections, how does all this weirdness add up to an unhackable network? Well, it's because the security here isn't based on making math problems harder to solve. It's baked directly into the laws of the universe. The first rule of quantum security is simple. You can't cheat. There's a fundamental principle called the no cloning theorem, which basically says you cannot create a perfect copy of an unknown qubit. You can't just copy and paste it like a regular file. This single rule makes a hacker's job of intercepting and stealing data pretty much impossible. And here is the truly brilliant part. If a hacker tries to eavesdrop, to intercept a qubit and measure it to see what it says, the very act of looking at it changes it. It's like trying to read a secret message written in ink that vanishes the moment you shine a light on it. That disturbance leaves an unmistakable trail. An error is introduced, and the system knows immediately that someone is listening in. It's self-policing. So what we're looking at is an entirely new kind of network, a hybrid of quantum computers, special repeaters, and even satellites. The whole point is to achieve what experts call information theoretically secure communication. Now, that's just a fancy way of saying it's secure not because it's hard to break, but because the laws of physics themselves say it is impossible to break without getting caught. Okay, so it sounds perfect, right? But here's the catch, and it is a monumental one. Actually building this thing is one of the greatest scientific challenges of our time, because harnessing these incredibly delicate quantum states over any real distance is really, really hard. So there are a few massive problems. First, qubits are extremely fragile. The slightest bit of noise from the environment, a little vibration, a temperature change, can make them lose their quantum magic. That's called decoherence. Second, the particles of light used to carry the information can just get lost or absorbed in the fiber optic cables. And finally, remember that no cloning rule? Well, that also means we can't just amplify a weak signal like we do with classical data. So instead of fighting these problems head-on, scientists are getting clever.
They're using quantum mechanics itself to get around its own limitations. The key isn't to send the fragile qubit itself over the whole distance, but to move its information using a pretty mind-bending trick.
The solution is a device called a quantum repeater. Think of it like a relay race. Instead of having one runner try to go 100 miles, you have a chain of sprinters. Each repeater creates a short, perfect entangled link with its neighbor. Then, using a process called entanglement swapping, they pass that entanglement down the line, stitching all the short links into one long, unbroken chain from the start to the finish. Once you have that long-distance entanglement established, you can perform quantum teleportation. Now hold on, this isn't Star Trek. We're not beaming matter across space. We're using that entangled connection to transmit the exact state of one qubit to another, faraway qubit. The information arrives instantly at the destination, and the original is destroyed in the process. So it's less of a transporter and more like a perfect cosmic fax machine. And I know this sounds like pure science fiction, but it's not just a far-off dream. Researchers actually have a tangible, step-by-step roadmap for making the quantum internet a reality. The plan is basically a 3-stage rollout. You start small, connecting the quantum processors inside a single machine. Then you connect multiple machines in the same building, creating something like a quantum data center. And then the final, most ambitious step is to connect those data centers across cities, countries, and eventually the globe. Of course, this journey is going to require just an immense amount of innovation. Moving from a perfectly controlled lab to a complex global network that has to deal with huge distances and different types of hardware, well, it's a staggering challenge. It's wild to think that more than 50 years ago, the first step into our connected world was a tiny broken message. A student was trying to send the word login over the ARPANET. He typed L, he typed O, and the whole system crashed. So the very first message on the internet was just low. That was the humble beginning of everything. And that just makes you wonder, right? As we stand here on the verge of this brand new era, with a technology built on the very fabric of reality, what's it going to be? What will be the first message sent on the quantum internet? What will be our low for this new unhackable frontier?